So we talked about spectrum from hydrogen gas. When you pass electric discharge through a hydrogen gas, it emits light, but if you disperse that light by a prism or a grating, you find that there are only specific wavelengths that are present. And to understand that, one has to deviate from classical physics, and Niels Bohr made the best attempt, very successful attempt, by making certain assumptions, and we wrote those assumptions. So according to that, the electron goes in circular orbit around the proton. That is necessary, otherwise it will just fall because of Coulomb attraction. But then the most important thing, there are certain specific orbits in which it gets a license to defy Maxwell's laws and classical physics laws. It does not radiate even though there is an acceleration. And how those stationary orbits are found, for that we had the third postulate, and that was the angular momentum of the electron, which is mass times velocity times the radius of the circle about that proton. That should be integral multiple of Planck's constant divided by 2 pi. So this decides which orbits are stationary orbits in which it does not radiate anything. Okay, so let us try to first calculate the energy of this system, proton, electron, hydrogen atom system, for different values of n. So we have, let's say we have this proton here and electron here, and that electron is going inside a circle of some radius r corresponding to this integer n. So the equations should be acceleration, which is v square divided by r. If this speed is v, then the acceleration is v square by r. The force towards the center, that is Coulomb's force, q1 q2 by 4 pi epsilon naught r square. So this is it, E square over 4 pi epsilon naught r square. This is the force, q1 q2 by 4 pi epsilon naught r square. This is the force, and this force should be equal to mass of the electron times acceleration, which is v square divided by r. So you have E square over 4 pi epsilon naught r. This is equal to mv square. So you can write kinetic energy half mv square in terms of r. So kinetic energy is half mv square, which is E square over 8 pi epsilon naught r. And potential energy you can write, potential energy is q1 q2 divided by 4 pi epsilon naught r. Here electron has negative charge, proton has positive charge. So this potential energy is, let's first write this, q1 q2 over 4 pi epsilon naught r, and that is equal to minus E square over 4 pi epsilon naught r. So the total energy U, which is kinetic energy, and plus potential energy. So kinetic energy is this much, potential energy is this much. You add these two and you get minus E square over 8 pi epsilon naught r. So this is the total energy. In terms of r, we still do not know what is this r. Okay. To get this r, we should use this equation, L is equal to n times h cross. So the angular momentum is m times v times r. That should be equal to n times h cross. So eliminate v from these two equations, this equation here and this equation here. All right. So here you have E square over 4 pi epsilon naught r. So E square over 4 pi epsilon naught r, this one equal to m times v square. So this is equal to m times v square. So from these two equations eliminate v. So get v from here and put here. So this will be equal to m v square n h cross divided by mr square. So this is equal to n square h cross square divided by mr square, and therefore E square over 4 pi epsilon naught is equal to, I am working with this is n square h cross square divided by mr. So what is 1 by r from here? 1 by r is equal to, so I am taking this m here, so m E square and divided by 4 pi epsilon naught, and then I am taking this thing on this side, n square h cross square. So that is 1 by r. And put this 1 by r in the expression of this total energy. So the total energy U is minus, and then you have this E square over 8 pi epsilon naught. So let me write E square over 2 into 4 pi epsilon naught. So this is E square over 8 pi epsilon naught multiplied by 1 by r. 1 by r is here, so I have to multiply by this. So multiply it by m E square, and then in denominator 4 pi epsilon naught, so square of this, and then this n square and h cross square. So h cross square and n square. This E square into E square you can write as E4. So this expression is finally U is equal to minus m e to the power 4. So minus m e to the power 4 divided by 2 into 4 pi epsilon naught square h cross square, and then 1 over n square. Right? Now this quantity here, this quantity, this is mass of electron, a fixed quantity, charge of electron, a fixed quantity, 2 into 4 pi epsilon naught, fixed quantity, h cross Planck's constant divided by 2 pi, fixed quantity. So this has got a particular value, and if we put all those values there, mass of the electron, charge of the electron, epsilon naught, all those values put there, Planck's constant, and calculate, that turns out to be almost 13.6 electron volt. So the energy is minus 13.6 electron volt and divided by n square. So you can say this is UN. Okay. So, and how does R vary? We have this 1 by R here. So you can write the expression of R also. R is 4 pi epsilon naught h cross square divided by m e square, and then multiplied by n square. This R you have to take reciprocal. So 4 pi epsilon naught h cross square n square and m e square. So that is R. So this is energy and this is radius, and this quantity once again is just a number, and that number if you put all those values, that turns out to be 0.053 nanometers times n square. So you can say this is Rn. So these are the radii. These are the radii of those special orbits, stationary orbits. If electron chooses to be in one of these circles with these radii, it will not emit anything and it will continue in that particular orbit. And in that particular orbit, the total energy, kinetic plus potential, will be given by this expression. So, how do I picture this hydrogen atom? The picture is, the proton is here, and then there are certain allowed orbits. This is the smallest radius, n equal to 1, this expression here, n equal to 1 gives you the smallest radius, and that radius is 0.053 nanometers. By the way, this is known as Bohr's radius, Bohr radius, and we show it by the symbol A0. So, this radius here is Bohr radius A0. So, this is one allowed orbit, smallest allowed orbit. Then the next stationary orbit is 4 times A0, because n equal to 2. The next one is n equal to 2, and this is n square here. So, the next orbit will have radius 4 times this, so something like this. Four times this, 4 A0, where A0 is 0.053 nanometers. Doesn't look like circle, but you always assume whatever I draw is a circle. And then the next one will be 9 times A0, so like that. So, you have n equal to 1, n equal to 2, n equal to 3, these are stationary orbits. And what are the energies? The energy of this n equal to 1 orbit, the energy is U equal to minus 13.6 eV, n is equal to 1. Then next, n is equal to 2, the energy is minus 13.6 eV divided by 4, that is minus 3.4 eV. Then n is equal to 3, that bigger one, 9 A0, radius 9 A0. So, U will be, energy will be minus 13.6 eV divided by 9, and that is how much? 1.5, approximately 1.5 eV. N is equal to 4, you will have U is minus 13.6 eV divided by 16, that is 0.85 eV, and so on. So, this is how you can write all those energies. So, how is that related to wavelengths that we observe from a hydrogen discharge tube? So, that is, when electron jumps from one orbit to the other orbit, the fourth postulate, it emits light, and that light pulse that will be emitted will have energy which is difference of energy in those orbits. So, let me do something, another picture. I will show all these energy levels just by drawing lines. That is how traditionally people do it. We draw a line, horizontal line, and say that this represents minus 13.6 eV. So, in vertical direction energy is going up. So, this corresponds to n equal to 1. And then n is equal to 2 is minus 3.4 eV, that will be, let us say, somewhere here. This is n equal to 2, it is minus 3.4 electron volt. N is equal to 3 is 1.5 with a negative sign. So, 1.5 will come somewhere, let us say somewhere here. This is n is equal to 3, and this is minus 1.5 eV. Then you have 0.85 eV, n is equal to 4, and so on. So this way it will increase, and when n is very large, n is say infinity, then this becomes 0, minus 13.6 divided by n square. So 0 corresponds to this 0 corresponds to say n is equal to infinity, and that means the radius is very, very large as compared to the Bohr radius. That means this electron has gone out. It is not bound to the proton. So that system where electron and proton are widely separated, that energy we are taking at 0, and with respect to that all these energies are given. So what happens when this electron going in an orbit makes a jump to another orbit with lower energy? For example, if it is going with this circle n equal to 2, and then suddenly it makes a jump and goes here. So the energy was minus 3.4 eV, and when it jumps, its energy becomes minus 13.6 eV. So what is that extra energy that it should emit? Okay, so if it goes from say n equal to 2 to n is equal to 1, this extra energy is n equal to 2 to n equal to 1. So initially it had minus 3.4 eV energy, and then finally it has minus 13.6 eV. So this is 10.2 eV. It should emit 10.2 eV in some form. And in what form? It emits in the form of electromagnetic radiation. So how is that electromagnetic radiation? Light is also electromagnetic radiation with proper wavelength limits. So how is that energy related to this electromagnetic radiation? Another quantum idea, another quantum physics idea. This light can be regarded as a collection of particles. Light can also be regarded as a wave of certain wavelength and certain frequency. When we talk of a wave, we have something in mind which oscillates in time, and therefore we talk of frequency. When we have a particle in mind, we do not talk of frequency. Nothing is oscillated if we have particle in mind, we talk of particles. So waves have frequencies, waves have wavelengths. If you look at the pattern at certain instant in a space, you find that that quantity is large at one place, then smaller at some other place, then smaller at some other place, again it increases. So at any instant in space there is a periodicity, and that periodicity is wavelength. In time there is a periodicity. If you focus at certain location in space, then that quantity that varies with time and it oscillates, and how many times it oscillates per second is the frequency. So for a wave we talk of wavelength and frequency, and for a particle we talk of its kinetic energy, its potential energy, its total energy, its linear momentum, and all that. So this is another quantum idea, quantum physics idea. Light sometimes shows up as a collection of particles. You can count how many particles are there, and each particle has got an energy and a linear momentum, particle characteristics. So let me write that. So light can be treated as, light means any electromagnetic radiation, any electromagnetic radiation. If the wavelength lies in that visible range 400 to 700 nanometer, we generally call it light. and if it lies outside that, we call it radiation. Light is also radiation, electromagnetic radiation, so that in that sense. So light can be treated as a collection of particles. Okay, when this tube light, I put this tube light on, I can say that this tube light is emitting one photon, then next photon, and then next. So these particles are called photons. So it's that character. So you can count how many particles are there. So these particles of electromagnetic radiation, they are known as photons. So for each photon you can ask what is the energy and what is the linear momentum. So it has got an energy and a linear momentum. These photons, each photon has got some energy E and a linear momentum P. These are particle characteristics. At the same time, this light can also be treated as a wave. And when it is treated as a wave, then the characteristic things are wavelength and frequency. So the same object light or EM radiation, that same object can be regarded as a collection of particles, a collection of photons, or a wave. When you talk in terms of photons, then you talk of energy and momentum. When you talk in terms of waves, you talk of lambda, wavelength and frequency nu. In fact, this is a very, very old debate, you know. Newton in very initial time, 17th century, he put forward this idea that light is a collection of particles. And the Christians, Huygens, that put forward the idea light is a wave. And experiments were to decide which description is correct. So when in 1801, 1802, 1803, those interference and diffraction experiments were done, it was established that light is wave. I can show you a diffraction experiment which shows that light is wave. So I have here a source of light. This is a laser, green laser. So this will, when I put it on, it will just send some green light, and which will fall wherever it finds an obstacle. And then I have a wire. I don't know if you can see the wire. In this gap you have a thin wire here. Okay. So if I send this light on this wire, if this light, this green light, if this light falls on the wire, then on the other side of the wire, light goes in certain selected directions only, and in between those two selected directions no light goes. That is because of diffraction, that is because of the wave character. So you just see on the screen, I am just putting it there, and you see in the screen how all this diffraction takes place. Okay. So I have put this laser light on, and then I am bringing this wire in the path of that laser light. Okay. So it is not falling on the wire now, and here it is falling on the wire. Here it is falling on the wire, if you can see. And on the other side of this wire, where it is falling on the wall, how it appears there, that you see in the next frame. So you can see that light is reaching certain points of this screen, and at certain points no light is reaching. So you see a central bright spot, and after that you have alternate bright green things, and then a dark space, again bright green, again dark, and so on. on both sides. We call it diffraction fringe. And why light is reaching at certain points and not reaching at certain points in between? That is because of the wave nature of light, wavelength of light, that decides the width of this wire, that decides where light will go, where light will not go. You have constructive and destructive interferences in different directions, making this pattern. Such experiments of diffraction and interferences established beyond doubt in early 19th century, 1801, 1802, on those times, that light is a wave, it behaves as a wave. Okay? So, light is a wave. Light is also particle. We have another sets of experiments, I am not doing it here, photoelectric effect, then Compton effect, right? What is Compton effect? A very nice experiment. Let me describe that. So, if you have some let us say some atom or some collection of atoms here, and you have electrons there, and you send a light of or a radiation of wavelength lambda. Generally this is done with X-rays. So, some wavelength lambda here, and that X-ray that falls on this system, and on the other side it emerges as X-ray of wavelength lambda prime, which is slightly larger than this wavelength. This is known as Compton scattering. And there is a certain relation between this angle theta and the difference between lambda and lambda prime, and how that relation can be obtained from equations. That equation can be obtained from equations if you assume that this electromagnetic radiation, this X-ray which is coming with wavelength lambda, has got a particle character, and each particle, this is a collection of particles, and each particle has an energy which is hc over lambda. H is the Planck constant, c is the speed of light, and lambda is this lambda. So, if you treat this radiation as a collection of particles, each particle having this energy and each particle having a linear momentum p, which is h divided by lambda, and apply your equations of collision of two particles. Here you have an electron, this X-ray collides with an electron. So, electron is one particle and this X-ray is another particle. So, these are the equations for energy and linear momentum. So, when it hits this electron will go with some velocity v at some angle phi, and mass of this electron is, let us say, m. Then you can write linear momentum conservation in this direction, x direction. And the linear momentum conservation will tell you this initial linear momentum is h over lambda, and this is equal to h over lambda prime. I am talking of this momentum in x direction, so x component, h over lambda prime is the momentum, and then cos theta, and plus m into v into cos phi, m into v into cos phi. And in y direction, the initial linear momentum was 0, so that final linear momentum should also be 0. So, you have h over lambda prime sin theta. So, h over lambda prime sin theta, and that should be equal to, so m into v into sin phi. And finally, the energy conservation, here the energy is hc over lambda. So this is hc over lambda, and here the energy is hc over lambda prime and plus half capital mv square. So see how I am using the particle dynamics here. This X-ray is treated as a collection of particles, a collection of photons, one photon colliding with one atom and one electron at a time. So we are writing the linear momentum of the photon, the energy of the photon, and doing all kinds of particle dynamics. And when you solve these equations, you get the correct observed relation between this lambda prime and this lambda. So light can be treated as particle, light can be treated as a wave, and the relation is given by these equations. The particle characteristic, energy and linear momentum are related to the wavelength lambda or frequency. This is also equal to h times nu. Okay, so the wavelength, frequency are related to energy and linear momentum. So now we are ready to understand how hydrogen emits only those 4 specific wavelengths, and that will be our next lecture's topic.